么下一个呢，有请我们的这个来自匈牙利的 Ferenc Domoki 教授。他是我们匈牙利塞格德的医科大学的获得的博士学位。他的研究呢主要集中在脑循环方面。那么获得博士学位以后呢，也在巴瑞教授课题组呢从事微循环相关的一些工作。在2012年呢，独立组建课题组，然后从事新生实验方面的研究。那么最新的研究方向呢，就是关于氢分子在新生脑缺血疾病方面的一些研究。有请我们的Domoki 教授。Perhaps Domoki, please start.
Thank you so much for the introduction, and thank you so much for the invitation. I'm really grateful to be here, and I would like to present our studies. Sorry. Okay. So we heard a lot about hydrogen today. Maybe we didn't hear much about hypoxic ischemic encephalopathy of the newborn. So I thought that I would like to start with that to make you comfortable and make you acquainted with this clinical situation. So this graph shows the global burden of disease worldwide, and on the Lancet homepage. And you can see that if you consider the life years lost to disease plus the life years affected by severe disease, life quality affected by severe disease, then neonatal diseases comprise a large percentage of the global burden, more than 7%, which can be comparable to, for instance, ischemic heart disease of the human population. And hypoxic ischemic encephalopathy is more than a third of the neonatal burden of disease. So this is somewhat confusing in the nomenclature, and they use these terms interchangeably, however they're not. So when I'm saying asphyxia or perinatal asphyxia, that's an insult that can cause the clinical presentation of a subacute brain damage. And this acute brain damage presentation is called in the literature correctly as hypoxic ischemic encephalopathy. But the real problem is not only the acute loss of life due to the brain damage, but the survivors will develop, in many cases, approximately 40% of the cases, severe neurodevelopmental outcome, which can be assessed only around 1.5 years of life. What is the cause of the brain damage? Really quickly, due to the lack of proper respiration through the fetal circulation, hypercapnia, hypoxia, and severe acidosis develops, which will eventually cause the loss of cerebral blood flow autoregulation, and this will lead to hypoxic and ischemic brain damage. The clinical diagnosis of hypoxic ischemic encephalopathy is really simple. You need to see at least one sign of recent asphyxiation and one sign of brain damage, and then you can make the diagnosis. The brain damage developing during hypoxic ischemic encephalopathy can be different. One of the most common causes when severe shorter ischemia develops is affecting mainly the basal ganglia and the thalamus, whereas longer ones can cause perirolandic watershed injuries. The good news about this devastating disease that after the initial asphyxiation, on this figure you can see the accepted pathophysiological sequence of hypoxic ischemic encephalopathy. So after the acute phase of hypoxic injury, including a large amount of oxidative stress and immediate cell death, there is a recovery phase, but this recovery phase is paralleled with ongoing pathology which will lead to eventually the presentation of so-called secondary energy failure, mostly due to accumulating mitochondrial damage. However, this offers a therapeutic window when neuroprotective treatments can be developed. The management of hypoxic ischemic encephalopathy, and I'm not going to go through all of these, is largely supportive therapy. And in the last 15 years, therapeutic hypothermia, cooling of the newborns for 72 hours has been developed. However, you can see that the current meta-analyses show that the numbers needed to treat is around 7, which means 7 babies need to be cooled to decrease mortality and severe neurodevelopmental outcome by 1. So it's still incompletely solving the problem. Our experimental model is the newborn pig, and I just showed 2 figures. Why is this a good model? For one, in humans and in pigs, there is a growth spurt of neurons right around birth, which is very much matching. So therefore, the piglet at birth is corresponding to the term newborn around 38 weeks of gestation. In our model, we use simulated asphyxia by ventilating the animals with hypoxic hypercapnic gas mixture, simulating the respiratory failure. And you can see the changes in the oxygen saturation and the acute reaction in the stress reaction in the blood pressure and the heart rate. Very severe ischemia in the cortex did not develop during this time. The blood gases show that the clinical criteria for severe asphyxia are holding up: severe hypercapnia and acidosis, and more than 15 decrease in the basic SAS could be determined. I'd like to point out that it's when you do a preclinical model, it's important to implement the safe supportive therapy what is being implemented, because otherwise you may have an effect of your drug or your treatment against nothing, but against the currently clinically supported therapy you may not be precise. So we do all these things to try to make the best supportive therapy, and it developed quite a lot over the week. So we even control for electrolytes, glucose, and so on. And treat the seizures when they grow up. We use continuous electroencephalography to look at the brain electrical activity, and we measure power spectrum density and other electroencephalographic measures to determine outcome. As the main areas affected, we focus on the basal ganglia, the thalamus, and the hippocampus to determine neurological damage. And in the background of this is the real objective, of course, that whether molecular hydrogen in this translational preclinical model can show neuroprotection or not. In our model, we use inhaled hydrogen, and on this slide I'd just like to show that inhalation of this 2.1% hydrogen causes a rapid accumulation of hydrogen in the cerebral cortex. This has been measured with hydrogen-sensitive microelectrode, and the hydrogen levels go back to baseline quite quickly upon cessation of inhalation. This was in a control experiment. And in our first experiment, we looked at 24 hours the outcome. in 3 groups: control, asphyxiation, and asphyxiation with 4-hour treatment, because at that time we saw that this is the most important time for combating oxidative stress. And we had a positive outcome with EEG, and also a positive outcome with the hydrogen. So we were quite happy with this result, and we showed that really oxidative stress marker like 8-hydroxydeoxyguanosine was lessened in our animals. Also, microglial activation was smaller. However, this made us to embark on a more complicated study when we wanted to combine the hypothermia treatment with hydrogen. So 4-hour hydrogen ventilation starting right after asphyxia, combining with therapeutic hypothermia, and we also elongated the observation to 48 hours to fully see the whole story of the secondary energy failure. And we used a little bit more severe hypoxia, 4%. And this is just to show the implementation of hypothermia with 2-hour delay, because at that time, when this study was done, the babies could be waited up to 6 hours before implementation of the cooling. And unfortunately for us, we saw that on the EEG already that there was a limited or no effect of the hypothermia and not additional effect of hypothermia plus oxygen. This figure on the right shows visual evoked potentials, 100 times repeated visual stimulation, and you can see that after asphyxia the effect is largely gone. And similarly, the neuropathology histology measurements showed that, for instance, in the putamen, there was a very, very large number of percentage of damaged neurons you can see here, and hypothermia didn't offer much release, and hydrogen was not effective. So quite recently, we were discouraged after publishing this negative results, and then we recently embarked one more time to study the hydrogen in a 48-hour model. We concluded that the 4% hydrogen was 4% oxygen was too severe hypoxia to save the brain under any kind of circumstances, so we went back to the 6% oxygen. And now, since in the meantime the literature, as today we saw it many times, there are long-lasting effects of hydrogen, we decided to provide the hydrogen ventilation throughout the 48-hour period. And also the hypothermia treatment was started immediately after the asphyxia, because now babies who are born, they don't start really the active cooling, but they let them spontaneously cool. So we thought that let's give it a maximum shot for the hypothermia to do what it's best to do, and compare whether 48-hour hydrogen inhalation versus 48-hour hypothermia is doing any good. And these are just showing the, you can see the effect of cooling, how it decreases the heart rate, and after rewarming the heart rate returns to normal. Otherwise, the blood pressures were within the normal range for this species. And the EEG shows, I don't want to go into and can't go into every detail, but this is showing the spectral entropy of the EEG signal. which means that how complex the signal is. Usually ischemia and asphyxia makes the signal less complex, and it looks like that hydrogen treatment was having an advantage here. And with the histopathology, and these are very fresh results, I would like to show that probably because our supportive therapy got better, we don't see such a large damage in the basal ganglia anymore. However, in the thalamus, we see a huge lesion, and hydrogen and therapeutic hypothermia were equally effective to prevent this neurological damage. So the conclusion that under optimal conditions, the hydrogen can be as effective as therapeutic hypothermia to mitigate neuronal injury in this model. And clearly further studies are warranted. Thank you very much for your kind attention.
Professor Domoki, thanks for your wonderful presentation about the thermal hydrogen therapy. It's very, very cool. 因为时间掌控的还比较好啊，我们允许提一个问题 ，reward one question。简单的小问题。Any question? 好，如果没有的话，那么OK， 泰勒。
Hypoxia?
No, we didn't consider in this model preconditioning because it's rarely the situation that women who go into labor would know in advance that there's going to be a complication. But actually, I think in a rat experiment, it has been done when the pregnancy was complicated with infection, ascending infection. And in that case, hydrogen was preventive. And this is actually what we would like to do, because many of the cases, this is not clearly just an asphyxia, but infection of the placenta and asphyxia on top of that. So that's clearly one way to step forward. And thank you very much again.
Okay, thanks. That's all.
And if you have any questions afterwards.